Okay, hi, I'm Rahat, and I'm going to be talking about this natural product which I've been researching a little bit about. And there is scientific interest in natural products like this found in biological systems of marine organisms. So my focus is on a product found in a type of algae called Symbiodinium, which lives in tropical sea anemone and jellyfish and other marine invertebrates. So symbioimine and its variant neosymbioimine are zwitterionic natural compounds derived from Symbiodinium, and they could be of use for medical chem because of their potentially useful effects. So symbioimine inhibits differentiation of precursor osteoclast cells into mature osteoclasts. Since mature osteoclast cells are cells that degrade bones, symbioimine could be incredibly useful to prevent bone thinning, so as a treatment for conditions like osteoporosis. So uh, it was also observed to have some inhibitive effects against cyclooxygenase 2, which means slight pain-killing effects. So it also has potential as a new NSAID or similar painkiller. So with the similarities of symbioimine and neosymbioimine, the low toxicity exhibited by both of them and their anti-osteoporotic activity, these compounds could be used to develop like efficient anti-osteoporotic drugs. Since the entire reaction scheme is pretty long, I'll skip through the mechanisms not really related to this year's content and stick to going in depth for more relevant stuff. So reactions including phosphorus, silicon, and sulfur. So starting with this molecule, we want to introduce an enoate ester, which is an alkene alpha to an ester, into the molecule by doing a Horner-Wadsworth-Emmons reaction, or a HWE. Although before we start the reaction, we have to prepare the phosphonate, which is done by reacting this triethyl phosphite with this alkyl bromide. So the lone pair on the phosphorus will attack this carbon alpha to the bromine, pushing electrons onto the bromine, which gets kicked off in an SN2 reaction. The bromide ion now attacks this carbon alpha to this oxygen, pulling away this ethyl group, and the electrons in this bond will go towards forming a phosphonyl bond, which you can see here, and we get our phosphate. So then we deprotonate this carbon alpha to the phosphorus in the presence of a base. In this case, we're using DBU in the presence of lithium because lithium helps to coordinate the deprotonation better, increases the expected yield of the reaction, which is important considering that the reaction scheme to produce neosymbioimine is very low yield. So it's nice to optimize the steps that we can. So after deprotonation using this base, we end up with the deprotonated phosphonate anion. In this form, the phosphonate anion attacks this aldehyde carbon, pushing the carbonyl electrons onto the oxygen. So now we have two ways that this reaction can go based on how the carbonyl was attacked by the phosphonate. The kinetically favorable route is this route here, and that's because that's just the way that the phosphonate would initially have bonded with the carbonyl. So while initially this may be kinetically favorable, the fact is that there is steric clash between having the bulkier groups on the same face. And on the bottom route, which is less kinetically favorable, there is less steric clash as the bulkier groups are on opposite faces. And because of how the entire reaction up until the product formation at the end is reversible, the slow product formation here, because of having unfavorable thermodynamics due to the steric clash, means that this will be the faster product to form because all the product generated up until here can just get reverted back and go all the way back around into the more thermodynamically favored system. So while in a kinetically controlled reaction, especially a reaction where each of these reaction arrows had one head, we could expect this top cis alkene to be the final product. In this case, because the reaction is thermodynamically controlled, we would expect a majority product from this transalkene. Following a deamination from the previous product, we use a silyl protecting group to protect the secondary alcohol. So this starts with an imidazole acting as a base towards this tert-butyl dimethyl silyl chloride, or TBS, with its nitrogen lone pair. So the imidazole attacks the TBS silicon, kicking off the chloride as a leaving group, resulting in a reactive intermediate which the alcohol can attack. The alcohol oxygen will attack the TBS silicon, removing the base, and the oxygen ends up with one too many bonds, giving it a positive charge. And in order to remove this positive charge, the OH bond will break, and the electrons from that bond will go towards the oxygen, giving us a protected molecule. Now that we have a protected secondary alcohol, we want to deprotect the primary. This deprotection will be conducted using an acid, and in this case we use camsulfonic acid. And an example of a fluoride-based deprotection is going to be shown later in the video. So the methanol oxygen here will attack a proton which are derived from the camsulfonic acid, and we end up with one too many bonds again on the oxygen. A methanol molecule oxygen lone pair is going to attack the silicon, making the silicon a good leaving group, allowing this oxygen-silicon bond to break to remove the charge from the oxygen. And so now we have our alcohol back, the primary alcohol. So there is a point to make about this reaction step, which is that if we left the reaction running long enough, the secondary alcohol, which we just protected, would also deprotect eventually, given time. The primary deprotection is a quick step, but the secondary deprotection takes longer. So what we can do is we can follow the progress of this reaction, or the depletion of the reactant, using TLC, and then once we see that all the reaction is finished, end the reaction there to prevent the secondary alcohol from becoming deprotected as well. And to remove all the CSA, we would have to, CSA being camsulfonic acid, we would have to buffer it out using a base. Next, we have a Dismartin periiodinane reaction, which is not this year's content, so I'm going to briefly skim it. But what we do here is that we add DMP to our product to turn the primary alcohol into an aldehyde. And this would be done in dichloromethane under room temperature condition. The next step is a stabilized Wittig reaction to convert our aldehyde generated in the previous step into an enal group, which is this group here. Similarly to the HWE, we need to generate a molecule to react with our aldehyde. So a unit of triethylphosphine here can react with our alpha chloroaldehyde, kicking off this chloride as a leaving group. So this gives us a phosphonium salt. A hydroxide group removes the hydrogen from the phosphonium salt, creating this ylidene. So effectively, the ylidene is the stabilized Wittig's version of the phosphonate that we would have generated for a HWE reaction. So the ylidene will attack the carbonyl carbon on the molecule, and the carbonyl electrons will go towards the oxygen. And this again gives us two possible routes that we can take. The upper route being the kinetically favorable option, as again, similar to before, this is just the way that the ylidine attacks the carbonyl with the two bulkier groups on the same face. So while this is the most kinetically favorable form, again, it's not the most thermodynamically favorable because of the steric hindrance from having two bulky groups on the same face. And so while this would be the fastest forming kinetic products, the product formed from this reaction is not going to be the major product just because of how slow it would be to form that final product because of that steric hindrance. Again, this reaction is thermodynamically controlled, so it is the thermodynamically favorable product which will be the major product in the end. And so this bottom route where we have less steric hindrance is going to be the favored route thermodynamically, because while you can have a majority of this upper route being formed, if it's slow to generate the product, then the product can just revert all the way through to the other route and quickly generate this major product. So this reaction has a yield of 88% of the E isomer product, and while typically this reaction would work at lower temperatures, despite having a lower yield, using a higher temperature will optimize the yield as this reaction is thermodynamically controlled. So this reaction, as I've mentioned many times now, is very similar to the HWE reaction, which makes sense considering the HWE is a adapted Wittig reaction, with a key difference in that the Wittig reaction produces a stoichiometric amount of triphenylphosphine oxide, which is really hard to get rid of, and the HWE reaction instead produces a byproduct which is easily soluble in water. So skipping ahead further into the reaction scheme, this is an example of deprotection of an alcohol using fluoride, which can be used in the place of stronger acids, especially in situations when strong acids would be undesirable because of the effect that they would have on other groups in the molecule. The fluoride source we use is tetrabutyl ammonium fluoride, or TBAF, which is a soluble form of fluoride that can be bought in THF. This is an important molecule because most forms of fluoride would not be soluble. So now, further in the reaction scheme is a sulfation reaction where we get both alcohols, oxygen lone pairs attacking sulfur trioxides, kicking off the pyridines. However, having both alcohols being replaced by sulfur trioxides is not what we want, because Neosymbioimine looks like this and only has one of these sulfate groups instead of two. So we would need to hydrolyze one of them. And so this process is called monohydrolysis and is carried out in methanol and water. When referring to the paper that details this synthesis by Varseev and Maier, it was shown that while monosulfation would be ideal, they mentioned that it was a challenge, and so it's likely that while they tried to do a monosulfation reaction, it didn't turn out great, or there was undesirable side effects, and so they decided to go through this route where they would sulfate both alcohols and hydrolyze one of them. So the amines lone pair here is going to pick up this proton, and the oxygen lone pair here is just going to do the same. We end up with here this quaternary nitrogen and this oxygen, which is cationic now because it has one extra bond. Having this water molecule's oxygen attack the sulfur will make the sulfur a good leaving group, allowing the OS bond to break, and we regenerate our alcohol here. Leaving this reaction running for too long would be an issue, as we can actually get both sulfates hydrolyzing if we leave this reaction running for too long. But as long as we track the reaction using TLC, we will know when the product has become Neosymbioimine, and we can stop it from over hydrolyzing. So now we get our natural product Neosymbioimine, which is the target of this synthesis.